For thousands of years we have looked to the skies. We never found a definitive answer to a single question. Are we alone? We thought that search was finally over. But we were wrong. So terribly wrong. The James Webb Telescope locked onto a planet 124 light-years away and found something that was simply impossible. In its atmosphere was a molecule that on Earth is produced almost exclusively by life in our oceans. The signal's accuracy, 99.7%. But that is not the most incredible part. The concentration of this life chemical was a full 10,000 times greater than in all of Earth's oceans combined. This should not have happened. And so, this discovery gives birth to a far more unsettling question. If you too are thrilled by the possibility that our place in the universe is about to be shaken, then like the video and subscribe, because the greatest discovery in human history might also be our greatest mistake. Let's begin. For years, we imagined what it would be like to find life in the universe. Maybe we expected a radio signal, or perhaps an alien ship appearing in the sky. But the universe didn't send us a picture or a message. It sent a smell. And the James Webb, the most powerful telescope humanity has ever built, picked up that smell from 124 light-years away. This discovery fundamentally shook everything we thought we knew, because the rules of the search for life were rewritten that day. It all starts with a number, 99.7%. Stay with that figure for a moment. This is not the success rate of a minor surgery. It is certainly not the accuracy of a GPS satellite. Number 4. This is the probability that the most powerful telescope ever built by humanity has detected the chemical fingerprint of life in the atmosphere of a planet 124 light-years away from us. This is not a rounding error. It is not a measurement noise either. This is a whisper that our ancestors, who looked at the sky for 3,000 years, never had the right equipment to hear. It is something the universe is saying directly into our ear. To grasp what this number means, consider this. You flip a coin 10 times, and it comes up heads all 10 times. At that point, you no longer calculate probabilities. You don't think about luck. You pick up the coin, and you check if both sides are the same, because the human brain, even if not trained in statistics, understands that 10 heads in a row is not chance. Something else is happening. This is roughly what 3 sigma certainty, or 99.7%, means in scientific language. The signal is not behaving like random noise. It is behaving like something real. Something that continues to be there, no matter how many times the instruments are checked, no matter how many times they are roomies calibrated. ESO. What is at the center of this signal? The name of the molecule carrying this whisper is dimethyl sulfide, DMS for short. It is not an exotic compound. It is not a theoretical concept either. In fact, you are extremely familiar with it. If you have ever walked on an ocean shore on a cool morning as the tide recedes, and you breathed in that sharp, slightly salty, slightly organic smell, that smell is largely dimethyl sulfide. It is the breath exhaled by the ocean. It is what happens when microscopic algae called phytoplankton die and are broken down by bacteria. It is a gas that mixes into the atmosphere, and it tells the sky that something biological is happening down below. But this is where things get truly disturbing, because dimethyl sulfide doesn't just have one confirmed biological source on Earth. It has almost only biological sources. Volcanoes do not produce it in significant concentrations. The interaction of ultraviolet radiation with rock chemistry does not create it. Lightning does not create it. Laboratory experiments that have tried for decades to produce dimethyl sulfide purely through geological or atmospheric chemistry have at best produced parts per billion. In other words, trace amounts. Yet, what Webb detected on K2-18b was parts per million. The difference between these two numbers is not a rounding error. It is a massive chasm into which all known non-biological processes fall and can never return. What the Cambridge team detected, in other words, is a molecule that on Earth has always meant one thing, and no known process other than life has ever been seen to produce it on the observed scale, 99.7%. What makes this incredible discovery possible is an engineering marvel, the James Webb Space Telescope. But Webb does not take pictures of planets like a camera taking a photograph of a landscape. You cannot see K218b the way you see the moon from your backyard, because the planet is too small, too far away, and lost in the overwhelming glare of the star it orbits. If you tried to directly photograph K218b, it would be like trying to see a single firefly 1 meter next to a lighthouse from a distance of 20 kilometers in broad daylight. The planet is, in the traditional sense, invisible. What Webb does is a far more subtle and equally extraordinary job. It reads light, the same way a barcode scanner reads a product at the checkout. Every molecule in the universe, every gas floating in an atmosphere, absorbs certain wavelengths of light and reflects others. Carbon dioxide swallows specific infrared frequencies. Water vapor has its own distinct pattern. Every molecule has a unique barcode at the quantum level that emerges when light passes through it. When K218b passes in front of its star, an event that lasts for about 8 hours every 33 days, a thin layer of starlight filters through the outermost edges of the planet's atmosphere and continues its journey towards Earth. Webb captures this light, splits it into a spectrum, and compares the resulting pattern to a library of molecular signatures built from laboratory measurements on Earth. To perform this operation, the telescope's mirrors are cooled to -233 degrees Celsius. This is just 40 degrees above absolute zero, the theoretical minimum temperature in the universe. This sensitivity allows it to detect a single molecule, hidden among a million other molecules. This is exactly what Webb did, and it did so from 124 light-years away. So what do we have? A number? 99.7%. This tells us the signal is too strong to be a coincidence. A molecule, dimethyl sulfide. This is a chemical produced almost exclusively by life on Earth. And an instrument, the James Webb Space Telescope. This shows us we have the technology to read this signal from so far away. When these three come together, they may be heralding the beginning of the greatest discovery in human history. But when the scientists at Cambridge University discovered this finding, they didn't pop champagne and celebrate, because 99.7% also means a 0.3% margin of error. And in science, when the claim being made is the most important claim in human history, 0.3% is not small enough. Not at all. This is precisely what separates this story from all the aliens found headlines you have seen to date. Because this signal could also come from a hellishly dead world. SO, K218b, is either a world teeming with life, vibrant and alive, or it is deceiving us badly. To solve this dilemma, we need to go deeper than how the telescope works. We must look at the planet itself, because K218b is not just a mystery because of the chemicals in its atmosphere, but with its very structure. With its very structure, it is an enigma in itself. Because K218b is a type of planet with no equivalent in our solar system. It's the most common type of planet in the galaxy. And 9, the most uniform world type orbiting other stars in the Milky Way. And in our solar system, we have exactly 0 of them. Not a single one. This situation is like a North American bird guide not mentioning sparrows at all. Scientists call them sub-Neptunes, and K218b falls right into this category. Its radius is 2.6 times that of Earth. Its mass is about 8.6 times greater. If Earth were a tennis ball on a table, K218b would be a basketball. Its volume is more than 17 times ours. And if you could somehow stand on its surface, gravity would press down on your body with roughly 2.5 times the force you feel right now. Every step would feel like carrying an adult on your back. Therefore, this planet itself presents a challenge for life. But that's not the main oddity. In 2021, researchers at Cambridge University proposed a theoretical class of planet they called Hycean. This name is composed of 2 words, hydrogen and ocean. The concept describes something previously not considered a serious candidate for life. A large planet with a thick hydrogen atmosphere and a global liquid water ocean covering its entire surface. No continents. No coastlines, no beaches, No tectonic plates rubbing together and pushing mountain ranges into the sky. No rivers flowing through valleys, because there are no valleys, just an ocean, stretching in every direction, to every horizon, from pole to pole. This ocean does not end. It just gets darker, colder, and heavier as you go deeper, until the pressure transforms the water into exotic high-pressure forms of ice, unlike anything you encounter in daily life. This is the world researchers believe K2-18b could be: hot, wet, boundless, and chemically rich. And, suspended above this hypothetical ocean, is an atmosphere dominated by hydrogen, the lightest element in the universe. K2-18b has enough mass to prevent this hydrogen from escaping into space. Therefore, it forms a thick atmospheric blanket, creating conditions where liquid water could exist on the surface. The star this planet orbits is a red dwarf named K2-18. Red dwarfs make up about 70% of all stars in our galaxy, and they are almost nothing like our Sunday. The surface temperature of K2-18 is about 3,184 degrees Celsius. Compared to the Sun's 5,500 degrees, it is quite cool. But red dwarfs have a violent side completely hidden by their modest appearance. They produce stellar flares, releasing energy equivalent to billions of nuclear bombs, with a frequency and ferocity that larger stars like the Sun can rarely match. K2-18b is only 21 million kilometers from its star. For comparison, Earth orbits the Sun at a distance of 150 million kilometers, so K2-18b is 7 times closer to a star that regularly erupts with radiation powerful enough to strip atmospheres and sterilize surfaces. But this is where the contradiction begins. K2-18b is located right in the middle of its star's habitable zone. Because its star is so dim and cool, the orbital band where a planet receives enough energy to maintain liquid water is much closer than in our system. The laws of physics are clear and precise. This planet receives almost the exact same total energy flux that Earth receives from the Sunday. This is not a coincidence. This is the inverse square law of radiation, combined with the specific brightness of a particular star, which places this specific planet in the right orbit to receive the right amount of energy to potentially sustain an ocean. The picture that emerges when all this information comes together is breathtaking. We have a world that seems to possess all the fundamental ingredients necessary for the existence of life. The right star, the right distance, the right temperature, and chemical evidence with a 99.7% probability that it comes from life itself. But it is at this point that another number comes into play, making the story far more unsettling. The concentration of DMS in Earth's atmosphere is less than 1 part per billion. What Webb found on K2-18b was more than 10 parts per million. That's a difference of more than 10,000 times. This is not a modest discrepancy requiring a small adjustment in current models. This is a difference so large, it changes the very nature of the question. If there is life on K2-18b, how efficient must the biology be to produce this signal? And this is only one side of the story, because there is also the other side of the coin. And now comes the real shock. Because the amount of dimethyl sulfide, DMS, in K2-18b's atmosphere isn't just a little high, it isn't just a few times more concentrated, it is at a level that even Earth's most productive ocean regions could never imagine. It is a number that defies biology as we know it. And so, now you will see why this discovery has turned into a nightmare that keeps scientists sleepless. It all begins with a comparison. Let's make this crystal clear. The DMS concentration in Earth's atmosphere is less than 1 part per billion. Even in our planet's most biologically productive ocean regions, like the nutrient-rich upwelling zones off the coast of California, this number barely rises. The global average remains steadfastly below 1 part per billion. But the data James Webb found on K2-18b tells a completely different story. The concentration there exceeds 10 parts per million. This is not a modest discrepancy. This is a difference of more than 10,000 times. To put this in perspective, imagine a stadium with 100,000 people. At any given moment, A single person in that stadium is holding something that represents Earth's atmospheric DMS level. Now, multiply that stadium by 10,000. Imagine tens of thousands of stadiums, every seat filled. The DMS signal from K2-18b would require every single person in those tens of thousands of stadiums to be holding that sign. This is not a difference of degree. This is a chasm that completely changes the nature of the question being asked. Because such a high concentration requires a production rate that is simply UN IMAR Gina Bale, the phytoplankton cells in all of Earth's oceans, a number expressed by putting 21 zeros after 25, produce about 100 million tons of DMS per year. And this massive production leaves only a trace of 1 part per billion in the atmosphere. To maintain a concentration of 10 parts per million on K2-18b, the required biological production rate would need to be thousands of times greater than what all of Earth's oceans achieve. This seemed impossible, but that's not the real impossibility. The real impossibility lies in the DMS molecule itself, because this molecule is not persistent. On the contrary, it is incredibly fragile. On Earth, the atmospheric lifetime of dimethyl sulfide is roughly 1 to 2 days. Ultraviolet radiation from the sun directly attacks the molecule, breaking the bonds that hold it together. Other chemicals in the atmosphere virtually race to break it down. This combined effect means that any DMS molecule released into Earth's atmosphere has an average of 24 to 48 hours before it is broken down into chemically simpler compounds. The only reason it is detectable in our atmosphere is that the ocean's phytoplankton population is so massive and productive that it constantly and relentlessly replaces every molecule that is destroyed. K2-18b's hydrogen-rich atmosphere changes this chemistry slightly. The absence of free oxygen eliminates one of the destruction pathways. Models suggest that in K2-18b's atmosphere, DMS could persist for 10 to 100 days instead of 1 to 2 days. This is a significant extension. A molecule lasting 50 times longer means it needs to be produced 50 times slower to maintain the same atmospheric concentration. But this is where the arithmetic becomes inescapable. Even assuming the most generous DMS lifetime, 100 days, the production rate required to sustain concentrations above 10 parts per million is still far greater than what any known geological process can produce. The extended lifetime helps, but it does not solve the problem. The number is still too large for rocks, volcanoes, and photochemistry. This situation brings us back to biology, and a scale of biology that is difficult to comprehend. And just at this point, when scientists were about to breathe a sigh of relief, an alternative hypothesis emerged that shattered everything. A hypothesis that does not require life, and a hypothesis that explains almost everything. Every good mystery has a second suspect. The suspect in the K2-18b case is, in its own way, more disturbing than the first. The alternative to a global ocean of microbial life is not a quiet, ordinary planet. It is something closer to a depiction of hell, a world whose entire surface is covered not with water, but with molten rock. A churning, superheated magma ocean baking under a hydrogen sky. Models show that the greenhouse effect created by K2-18b's thick hydrogen atmosphere could raise surface temperatures to over 800 degrees Celsius. At these temperatures, rock does not remain solid. Basalt melts at about 1,100 degrees and granite at 1,200 degrees. In this environment, volcanic gases continuously erupting from the molten surface could interact with the hydrogen in the atmosphere, theoretically forming organic sulfur compounds, including dimethyl sulfide. The yields are small, the chemistry is inefficient, but a magma ocean is a process that operates continuously on a planetary scale over geological timeframes. So, it raises the possibility that the signal Webb detected could be coming from a world that is far from habitable. Yet, what truly strengthens this hellscape scenario is not what it can produce. It is something conspicuously absent from K2-18b's atmosphere, ammonia. This molecule consists of 1 nitrogen atom and 3 hydrogen atoms, and in any hydrogen-dominated atmosphere, with a significant nitrogen inventory and enough energy to drive chemical reactions, it should form easily and accumulate to detectable levels. This is not a theoretical expectation. Jupiter has ammonia. Saturn has ammonia. Uranus and Neptune have ammonia. Every major planet in our solar system with a hydrogen-rich atmosphere shows strong ammonia absorption features in its spectrum. But there is no detectable ammonia on K2-18b, none. Multiple research teams have analysed Webb's data and found nothing above the noise level at the wavelengths where ammonia absorption features should appear. This is where the magma ocean hypothesis cleanly explains this absence. When nitrogen encounters molten rock under high pressure, it dissolves into the melt rather than remaining in the gas phase. This process effectively purges the atmosphere of the nitrogen needed to form ammonia. SO, a planet with a molten surface, naturally traps its nitrogen underground, leaving a chemically depleted atmosphere, just as K2-18b's atmosphere appears to be. This absence ceases to be a puzzle and becomes a prediction made by the magma ocean model and confirmed by the data. So, the scoreboard looks like this. The magma ocean wins on ammonia but loses on methane. The ocean world wins on methane but struggles with ammonia. Each hypothesis has a blind spot that the other exploits. And, at this very moment, science cannot make a definitive choice between these two worlds, because there is one more thing that both shatters and strengthens both theories. And that thing, that incredible contradiction that simultaneously supports and refutes both theories, was methane. Because the James Webb Space Telescope detected methane in K2-18b's atmosphere. But this wasn't a trace amount. It was a concentration of about 1%. This meant it was a significant atmospheric component, equivalent to more than 25 times the amount of carbon dioxide in Earth's atmosphere. And methane has a problem with high temperatures. This is an indisputable fact. Above about 700 degrees Celsius, methane molecules break apart. The carbon-hydrogen bonds holding the molecule together cannot withstand this thermal energy. But, at the temperatures of 800 degrees Celsius or higher suggested by the models supporting the magma ocean hypothesis, methane should have been continuously destroyed, much faster than any geological process could replenish it. It should not have been there. At least, certainly not at the concentrations Webb measured. But it was there, standing stable and unmistakable in the spectral data. 1%. SO, the ocean world hypothesis explains the methane simply. Biological production by methanogenic microorganisms, or thermochemical processes, operating at temperatures compatible with liquid water. Both pathways work on a cool, water-covered world, but neither of these pathways can survive contact with a molten surface. The magma ocean hypothesis scores a point by explaining the absence of ammonia, but it immediately loses that point with the presence of methane. The story does not end here, because in the minds of scientists, there is a much newer and more painful memory. The phosphine incident on Venus in 2020. That year, when a group of astronomers reported detecting phosphine in the cloud layers of Venus using ground-based radio telescopes, the announcement was treated by most of the science press as an almost certain detection of biological activity. Because there were no known abiotic, non-living production pathways that could explain the reported concentrations of phosphine in the Venusian atmosphere, the paper was published in a leading journal. The lead researcher was cautious, but his excitement was palpable. However, within months, independent reanalysis of the same data revealed calibration errors in the original processing pipeline. What appeared to be a strong phosphine signal transformed into a much weaker feature under scrutiny. And it was understood that this weak signal also overlapped with the absorption of sulfur dioxide, which Venus has in abundance. SO, the claimed detection, did not survive contact with independent verification, and this event explains why the DMS detection on K2-18b is being met with such caution. The scientific community fears this ghost will reappear. Is this 99.7% signal on K2-18b another phosphine case? Another calibration error? Another false alarm? This possibility keeps even the most optimistic scientists awake at night. Because if something once again called the discovery of the century turns out to be data noise, the credibility of science could suffer an irreparable wound. However, the DMS detection on K2-18b has so far survived this contact. Two separate instruments, NIRSPEC and MIRI, independently captured the same spectral features. Two separate analysis teams working from the same raw data reached the same conclusion. The signal does not disappear or collapse when examined from different analytical angles. This is not proof. It is not 5 sigma. But it is a structure of verification that the phosphine announcement on Venus never had. This is why some researchers are taking the K2-18b result much more seriously. And, at this very moment of seriousness, in October of 2024, another blow came from a place no one expected. From comets. Researchers, reanalyzing archival data from the Rosetta mission that studied Comet 67P between 2014 and 2016, reported detecting dimethyl sulfide among the organic molecules seeping from the comet's surface. This directly proved that DMS could form in the organic ice of cold, radiation-processed cometary material before life, through abiotic chemistry. This seemed like a death knell for the life hypothesis, because if DMS can form without life, then the signal on K2-18b could also be geological. But it wasn't, because the amounts detected on Comet 67P were negligible when compared to atmospheric concentrations. Sustaining atmospheric concentrations above 10 parts per million on a planet would require such an extreme and continuous bombardment of comets that its other effects, the delivery of other volatiles like water and carbon monoxide, would be clearly visible in Webb's spectrum. But they are not visible. So, the comet discovery does not undermine the K2-18b biosignature case. On the contrary, it refines it. DMS can exist without life, but it cannot exist at these concentrations, in this chemical environment, and with this specific absence of accompanying cometary markers, without an explanation that goes far beyond any currently proven abiotic pathway. So what do we have? On one hand, a DMS signal that screams life, but the fact that this signal is too good to be true, and the memory of false alarms like phosphine, creates doubt. On the other hand, a magma ocean theory that could explain this signal, but this theory has a massive methane presence that it cannot explain. Every answer raises a new question. Every piece of evidence brings another contradiction. This is a moment at the very edge of science, where the data points to two completely opposite realities at the same time. SO. What path are scientists taking to solve this incredible dilemma? How can they make such precise measurements from so far away? How does this signal itself work? The answer lies in the hardware itself, in the cold heart of the telescope, and in the incredible engineering that placed it there. Because James Webb is not just an observation tool, it is also a time machine, and understanding how it works is the key to solving this mystery. But what is the key to solving this mystery? How can they make such precise measurements from so far away? How does this signal itself work? After the shocking, dizzying speed of part 2, it's now time to downshift a bit. Now, it's time to look under the hood, into the very depths of this incredible machine, at the technique itself. Because this discovery by James Webb is a revolution, not just for what it found, but for how it found it. It all begins with the telescope's location. To understand this, imagine trying to listen to someone whispering in a very noisy room. It's almost impossible. Your own voice, the surrounding noise, everything drowns out that whisper. This is the fundamental enemy of infrared astronomy, heat, which is noise. And James Webb was designed to listen to the faintest whispers of the universe. So, you couldn't put it in Earth's orbit, where Hubble circles 540 kilometers above us, because the Earth and Moon are incredibly noisy and hot in the infrared spectrum. Therefore, Webb was placed about 1.5 million kilometers away from Earth, at a gravitational balance point called the second Lagrange point, L2, in the direction away from the Sunday. This is a distance 4 times farther than the Moon. In this position, Webb can simultaneously place its massive 5-layer sunshield, the size of a tennis court, between itself and the combined radiation of the Sun, Earth, and Moon. This shield keeps the telescope in a permanent shadow. But even this is not enough, because the telescope's own temperature is also a source of noise. To hear these whispers, Webb's 6.5-meter primary mirror, composed of 18 hexagonal gold-coated beryllium segments, must be kept at about -233 degrees Celsius. This is just 40 degrees above absolute zero, the theoretical minimum temperature in the universe. If the mirror were to warm up by just a few degrees, the thermal noise generated by the mirror itself would completely mask the signals coming from planets 124 light-years away. This is one of the most challenging engineering feats in human history. And, without this achievement, the DMS signal from K2-18b could never have been heard. But achieving this silence is only half the battle. Once the telescope is placed in such a quiet environment, how does it read those whispers? This is where an ingenious method called transit spectroscopy, which we mentioned earlier, comes into play. You can think of it like a barcode scanner. When you pass through the checkout at a grocery store, each product has its own unique barcode. That barcode contains what the product is, its price, and all its other information. Every molecule in the universe also has its own unique barcode. This barcode shows which wavelengths of light that molecule absorbs and which it reflects. Water vapor swallows certain infrared frequencies, while methane leaves a completely different pattern. When K2-18b makes a transit in front of its star, which lasts for about 8 hours every 33 days, a thin beam of starlight filters through the outermost layers of the planet's atmosphere, and into that light, the chemical fingerprint, the barcode, of every molecule suspended in that alien sky is imprinted. Webb captures this imprinted light coming towards Earth. It then splits this light into a color spectrum with its instruments, like NIRSpec, the near-infrared spectrograph, which studies wavelengths from 0.6 to 5.3 microns, and MIRI, the CHG, mid-infrared instrument, which extends this range up to 28 microns. Just like a prism separates white light into the colors of the rainbow. The resulting pattern is compared with the known barcodes of thousands of molecules measured in laboratories on Earth. And if a match is found, you know that molecule exists in that planet's atmosphere. This is a far more clever method than taking a direct picture, because it gives us the power to inventory the chemical composition of an atmosphere we cannot see. So, Webb doesn't just say yes or no, it says what is there and how much, but how precisely. This is where the mind-boggling capabilities of Webb become apparent. To visualize this sensitivity, think of an Olympic swimming pool. It holds about 2.5 million liters of water. Now imagine adding just one drop of blue food coloring to this pool. Not a teaspoon, not a capful, just a single drop. Webb's sensitivity not only sees that single drop as a faint blue tint in the pool, it can specifically identify it as blue food coloring and distinguish it from red, green, or hundreds of other dyes that might have been added to the same pool. This is parts per million sensitivity. Webb can detect a single target molecule hidden among a million other molecules with this precision. This capability is incomparable to any telescope before it. The Hubble Space Telescope had given hints of methane and carbon dioxide in K2-18b's atmosphere, but, as the source text also stated, it was like trying to hear a whisper through a concrete wall. The signal was weak and far from certain. Webb tore down that wall, and it turned the whisper into a clear, understandable sentence. This is why the signal from K2-18b is being taken so seriously, because the instrument that brought us this signal is categorically superior to anything we have had before. So we placed the telescope in the right spot. Thus, we created an environment isolated from the noise of the universe. Then, we used the right technique. Through spectroscopy, we read the chemical barcode of an atmosphere we cannot see. And we did this with such incredible precision that we could distinguish a single drop of dye in an Olympic swimming pool. When these three technical mechanisms come together, they form the most powerful discovery tool in human history. But this is only one half of the equation. This is the hardware side. This is the triumph of engineering. What about the software? What about the human factor that interprets the data collected by this incredible machine? How does the scientific process itself work? Because even the most advanced technology cannot skip that final step of turning data into a discovery. And this step is sometimes even more complex, more challenging, and slower than the telescope itself. Because this step is about human doubt, past mistakes, and the search for absolute certainty. And that step, that final mechanism, is not the telescope itself, but the scientific process that uses it. Because this process operates with a search for absolute certainty, with a memory of past mistakes, and with a patience that can sometimes be frustrating. And this slowness, this bureaucracy, is actually a mechanism as important as the discovery itself. It is a safety system that protects the discovery. The first layer of this safety system is a bureaucratic mechanism. James Webb is the most in-demand telescope in the history of astronomy. In any given year, the total observation time requested by scientists worldwide exceeds the telescope's available hours by a ratio of about 4 to 1. So, for every hour of observation time, there are 4 hours of demand. You can compare this to a restaurant run by the world's best chef, where reservations are booked years in advance. Everyone wants a table there, but only those who present the most compelling and best-planned menu get in. To raise the signal on K2, 18b, from the 3 sigma level, 99.7% confidence, to the 5 sigma level, the gold standard required by the scientific community to confirm a discovery. The Cambridge team needs an additional 16 to 24 hours of observation time. This corresponds to 2 or 3 full transit windows, given K2, 8b's orbit of every 33 days. The team has made a formal application for this additional time, but this application has been placed in a queue along with thousands of other proposals from researchers studying everything from the formation of the first galaxies to the atmospheres of planets in our own solar system. Therefore, the potential confirmation of the answer to the most important question in human history may be delayed not by physics or technology, but by the standard administrative process of peer-reviewed telescope time. Allocation. The universe's hurry does not align with the committee's schedule. This may seem frustrating, but this slowness is a critical quality control mechanism that ensures the telescope's invaluable time is dedicated to the most promising scientific projects. The second, and perhaps more important mechanism, is the standard of evidence within science itself. The difference between 3 sigma and 5 sigma. And 5 sigma, this is not just a technical detail, it is a philosophical wall that science has built to protect itself from false positives. Think of it like a courtroom. 3 sigma 99.7% certainty is like strong evidence or beyond a reasonable doubt. It might be sufficient for a conviction in many cases, but 5 sigma is proof beyond all reasonable doubt. This means the probability of a result being a statistical fluke is less than 1 in 3.5 million. This is equivalent to flipping a fair coin and watching it come up heads 22 times in a row. This standard was not chosen arbitrarily. It was born from the painful lessons of the past, particularly from events like the ALH 84001 meteorite in 1996 and the phosphine on Venus case in 2020. In both instances, findings touted as evidence of life were later explained as either terrestrial contamination or calibration errors upon further review. These events taught the scientific community and institutions like NASA that the bigger the claims, the more overwhelming the evidence must be. So, when the discovery of the Higgs boson in 2012 or gravitational waves in 2016 was announced, these announcements were made only after the 5 sigma threshold was crossed. This is why the Cambridge team is so cautious about K2, 18b, why the language they use is of a moderation bordering on disappointment, because they carry this institutional memory. The fear of being wrong outweighs the fear of being slow, and this asymmetry is entirely rational given the historical record. This is not a weakness, it is science's greatest strength: skepticism. Finally, there is a conceptual mechanism we use to interpret the data of this discovery, and it comes not from hardware or statistics, but from life itself. The Gaia hypothesis, developed by British chemist James Lovelock. This hypothesis suggests that Earth's biosphere is not just a passive passenger on a planet shaped by geology and physics, but an active participant that regulates the conditions that make life possible. Dimethyl sulfide was central to this argument. Lovelock realized that DMS, produced in vast quantities by marine phytoplankton and released into the atmosphere, was not just a waste product. It was a chemical lever that the ocean's microbial ecosystem pulled, perhaps unintentionally, to influence the climate of the entire planet. The mechanism is as follows. DMS in the atmosphere produces sulfate aerosol particles. These particles serve as microscopic surfaces, or cloud seeds, on which water vapor can condense and form cloud droplets. More DMS means more aerosols, which means more clouds. More clouds mean more sunlight is reflected back into space before it can heat the ocean surface. This cools the ocean. A cooler ocean slows phytoplankton growth, which reduces DMS production, which reduces cloud formation, allowing more sunlight to enter and reheat the ocean. This is a self-regulating negative feedback loop, like a planetary thermostat that life accidentally built from its own metabolic waste. The connection to K2-18b emerges here. If a similar mechanism is at work on that distant ocean world, it would mean that the organisms on K2-18b are not just existing in a habitable environment, they are actively building it. The DMS signal would not just be evidence of life, but evidence of life engineering on a planetary scale. And this is the only consistent mechanism that could explain that massive 10,000-fold production difference. Perhaps K2-18b's ocean doesn't have to be thousands of times more productive than Earth's. Perhaps it has just evolved a much more efficient DMS cycle to regulate its climate. So what do we have? A telescope placed at the quietest point in the universe. A technique that reads the chemical barcode of a planet's atmosphere. A slow but reliable scientific process designed to interpret this data, learning from past mistakes and demanding absolute certainty. And finally, a conceptual framework from life itself that could explain how such an overwhelming signal is possible. All these mechanisms are pieces of this incredible puzzle. But what's truly exciting is the picture that emerges when these pieces come together, because K2-18b and worlds like it raise not just the question of whether there is life in the universe, but a much more fundamental question. What if we have been looking in the wrong place all this time? What if the universal formula for life is not Earth's? And what if the real explosion, the real revolution, is not in the telescope's data, but in the galactic map that data has redrawn? Because this new map shows us that. And then, the most incredible thing happened, because all these mechanisms, all these technical details, opened just one door, and behind that door, there was not just a planet, but a whole new universe. A universe where everything we knew, everything we searched for, everything we imagined was demolished. Because the real revolution was not in the telescope itself, but in the galactic map that the telescope redrew. And now, that moment of revolution is coming. Forget the calm, methodical pace of part 3. Now, fasten your seatbelts, because we are shifting to maximum speed. This is the moment everything changes. This was the end of a 30-year dream. For 30 full years, the search for extraterrestrial life revolved around a single holy grail, Earth 2. Science was locked onto this goal. We were going to find a rocky world. It would have a solid surface. It would have a thin atmosphere. There would be liquid water in basins between continents. It would orbit a star similar to our Sun, at a distance similar to Earth's orbital radius. In scientific papers, in grant proposals, in press releases announcing new discoveries, the term Earth-like was a mantra. It was a search for a small copy of the only formula for life we knew. But then came K2-18b, and it shattered that 30-year dream with a single data point. It was not a copy. It was not a variation. It was a fundamentally different category of world. And in that moment, it was understood that the universe was not asking us to produce Earth templates, because it was building something else entirely. And that something else could be where life is. Everything depicted in science fiction films, every novel written, every simulation made, was invalidated that day. Because the universe's imagination was far wilder than ours, and this was the greatest paradigm shift in history. But the real explosion was hidden in the statistical consequences of this discovery. The numbers went crazy. The numbers exploded. Because the target of the Earth 2 paradigm, rocky, Earth-sized planets in the habitable zones of sun-like stars, are relatively rare. The Kepler mission looked at 150,000 stars for 4 years and found them, but it did not find them in abundance, a handful. But sub-Neptunes? They were the most common type of planet in the galaxy. Every survey, every statistical analysis, every instrument systematically pointed at the sky gave the same answer. The universe overwhelmingly prefers to make planets in the size range between Earth and Neptune. Not Earth-sized, not Neptune-sized. Right in the middle, the range that includes K2-18b. A recent analysis pushed this number to an incre-dB scale. Roughly 70% of the 400 billion stars in the Milky Way are red dwarfs. That's 280 billion stars. And new data suggests that about 40% of these red dwarf stars could host sub-Neptune planets in their habitable zones. 40%. 40% of 280 billion. That means more than 100 billion potential Hycean worlds, just in our galaxy. This number exceeded the number of Earth-like planets we had been searching for in the sky for all of human history by thousands, perhaps millions of times. This was not just slightly expanding the search area. This was realizing that the search area itself was millions of times larger than what we had been looking for before. This was like searching for a needle and discovering that the haystack itself was made of gold. And in that moment, scientists understood we had to stop searching in scarcity because we were swimming in abundance. And at this very moment of abundance, the most shocking, most humbling truth emerged. Our solar system, on this new galactic map, was an anomaly, an exception. The normal we had been searching for billions of years was not us, because in our system, of that most common type of planet, those sub-Neptunes, there are zero, none. The most standard output of planetary formation is not present in our neighborhood. This is one of the most unsettling gaps in decades of planetary science research. This was an astronomical revolution. For centuries, we had seen ourselves as a standard, a model for the universe. We had assumed that other star systems should resemble ours. But we were wrong. We were in a state of great delusion. K2-18b and its billions of siblings showed us what the universe's normal was. And in that normal, we were not present. We were the strange kid of the galaxy. This discovery took all our hubris. It demolished all our claims of centrality. And it confronted us with the fact that the rest of the universe was built on a much different, much more common plan. They were not the anomaly. We were the anomaly. And this truth changed the course of science forever. Because we were no longer searching for another Earth, we were now searching for something much bigger, what the universe itself is. But the biggest revolution revealed by this new map was not just in the number or type of planets. It was in the concept itself. The very concept of the habitable zone died and was reborn that day. It was no longer that thin ring, a narrow orbital band where rocky planets could hold liquid water. It became a category, a huge, multi-dimensional concept containing countless subcategories. Any world where the physical and chemical conditions allow for continuous biochemistry, regardless of whether it bears any visible resemblance to Earth. Think of it this way. For centuries, miners searching for gold only dug in granite mountains, because gold had been found there before, and the geological logic of gold pointed there. But then someone took a sample from the ocean floor and discovered that deep-sea hydrothermal systems had been producing gold on a massive scale for billions of years, in a place no one had thought to look. Gold was not scarce. The search paradigm was wrong. K2-18b was the first sample from that ocean floor, and what it showed us was this. The universe had not produced a single template, a single path for life. It had produced countless paths, and we were only looking at one of them. This was not just a modest expansion, it was a fundamental renegotiation of the entire search strategy. The habitable zone was no longer a place, it was a potential, and that potential was in far more places than the map had shown. And then, that final, ultimate blow came. This was no longer about a single planet. This was the discovery of a legion, because Webb was not just looking at K2-18b. It was also observing, or planning to observe, other Hycean candidates, and the list went on and on. TOI 270d, orbiting a red dwarf about 73 light-years from Earth, smaller than K2-18b, but its mass suggests a significant water content beneath its atmosphere. LP 8909c, orbiting one of the coolest, smallest stars ever confirmed to host a planet in its habitable zone. GJ 1214b, Studied for over a decade, its featureless transmission spectrum has long suggested a high-altitude cloud or haze layer obscuring its atmospheric composition. But Webb's infrared sensitivity can penetrate that haze in a way Hubble never could. All three of these worlds share the basic architecture that makes K2-18b interesting. They are not rocky, they are not Earth-sized, and they all orbit stars that our sun-centric search paradigm has long considered hostile to life. And now, they are all on the short list. This was not a coincidence. This was a pattern. A pattern. And in science, a pattern is data. This was not one planet saying, maybe, but a dozen planets shouting, we are here at the same time. This was the scenario that changed everything. Let's assume that in the next 5 to 8 years, Webb studies a dozen Hycean candidates and 3 or 5 of them show DMS signals with varying levels of confidence. At that point, the question, is there life beyond Earth, does not wait for a 5 sigma from a single planet. It is answered by the statistical weight of converging evidence from multiple independent worlds. So what do we have? The collapse of a 30-year paradigm, the discovery of hundreds of billions of new potential worlds, the realization that we are a cosmic anomaly, the meaning of the word habitable, expanding forever, and an entire army of these new worlds appearing on the horizon. This new, vast, mind-bogglingly large map lies before us. But what is this map telling us? Is it just saying life exists? Or is it whispering a deeper, more fundamental, perhaps more disturbing truth? Because the silence of this newly discovered, potentially life-filled universe is far more frightening than the silence of the old empty universe. And the meaning of that silence, changed in that moment. Because that new map didn't just give us a list of potential worlds, it gave us back the universe's biggest and most disturbing paradox, 10,000 times sharper, 10,000 times louder than before. That silence was no longer the silence of an empty room. It was the eerie silence of a stadium packed with people, but where no one was speaking, and this was more terrifying than anything, because it forced us to ask the greatest question in human history. If the universe is full of life, then where is everybody? This was the Fermi paradox, that deceptively simple question the Italian-American physicist Enrico Fermi asked at lunch in 1950. And the discovery of K2-18b did not solve this paradox. It turned it into a monster. It sharpened it. It magnified it. The numbers, the figures, 400 billion stars in the Milky Way alone. 60 years. The long 60 years that the Search for Extraterrestrial Intelligence, SETI program, has been listening to the sky. For any form of structured electromagnetic communication, radio waves, laser pulses, and the answer was always the same. Silence. But now we had a new number. Tens of billions of K2-18b-like planets. Tens of billions of worlds potentially harboring life. This did not make the silence quieter. It made it deafening. Each additional world was another potential civilization, and each one should have announced itself somehow. But none of them did. How could this be possible? This was against logic. This was against statistics. This contradicted the very idea that the universe was full of life. This was a moment of joyous discovery, suddenly turning into a moment of existential dread, because this silence could only mean one of 3 things, and none of them were comforting. This was the Great Filter, that terrifying idea put forward by cosmologist Robin Hanson, a bottleneck in the developmental sequence from chemistry to civilization that almost nothing can pass through. And now, with the data from K2-18b, 3 nightmarish scenarios for where that filter might be stood before us. Scenario 1. The filter is behind us. The emergence of the eukaryotic cell, that complex nucleated cell that forms the basis of all multicellular life, may be such an impossible event that it happens once per billion years per galaxy. In this scenario, the universe is teeming with microbial life. But it is almost entirely devoid of complexity above the single-celled level. Bacteria everywhere, almost no animals anywhere, and civilizations are rarer than the rarest thing you can imagine. The DMS signal from K2-18b, if biological, would represent exactly this scenario. A life that begins, continues, but can never escape the ocean, can never build a fire, can never look to the sky. This was the best case scenario. And this scenario didn't just make us rare, it made us almost unique. And the silence made sense, because no one else had advanced far enough to send a signal. But this was also a very deep loneliness. Scenario 2. The filter is life itself. The emergence of self-replicating chemistry from a primordial ocean is not inevitable. It happened on Earth. But Earth may be such an extreme exception that it represents a single statistical accident in a universe of billions of failed experiments. In this scenario, K2-18b is a false alarm. The DMS signal has an inorganic explanation we haven't found yet. All those Hycean worlds are sterile. The Milky Way is a gallery of empty rooms. And we are not just rare. We are alone. Absolutely. This perfectly answers the Fermi paradox, because there is no one to send a signal. Scenario 3. The conversation ender. The filter is not behind us. It is in front of us. Civilizations are common. Intelligence emerges regularly. They spread across their planets. They begin to reach outwards. And then, at a stage we have not yet reached but are rapidly approaching, they end. Something destroys them. Something they did themselves. Or something they encountered. Or something that is an inevitable consequence of evolving technology. In this case, the great filter is extinction. And it is a universal feature of the developmental curve of intelligent species. This was the most disturbing scenario, because it didn't say what kills civilizations. It just stated that something reliably destroys them before they can leave a mark the galaxy can remember. And if this is the pattern, then we are not unique. We are just at an earlier stage than those who have fallen silent. We are next. But what if there was a fourth door? What if there was a way to escape all three of these nightmare scenarios? It was then that the biggest, most epic idea exploded. An idea that came from K2-18b itself. And this idea did not just solve the Fermi paradox. It made it meaningless. The planet is an ocean world. It has no solid surface. It has no continents. It has no volcanic islands breaking its global sea. And, in this environment, the development of a technological civilization is, by any means we understand, physically impossible. Fire requires a fuel-air boundary and an ignition source in an open atmosphere. Metallurgy requires accessible mineral deposits and the ability to heat them. Electronics require refined conductors and insulators assembled with precision instruments. An organism floating in a planet-spanning ocean, no matter how sophisticated its biochemistry, no matter how coordinated its collective behavior, cannot build a radio transmitter. It cannot launch a telescope. In any sequence of steps we can currently conceive, it cannot produce anything that could announce itself across interstellar distances. What did this mean? It meant this. If there is life on K2-18b, that life is invisible to SETI. It was always invisible, and it will always be invisible. It cannot signal us, because it does not have the mechanism to send signals. And this meant that 60 years of SETI silence could coexist with a universe full of microbial ocean worlds and tell us absolutely nothing about their existence. The tool we were using, radio telescopes, was calibrated for a very specific type of life, the transmitter building kind. And maybe that kind was the rarest of all. The dominant life form in the universe was not technological. It was microbial and invisible. And it was there all along while we were looking, producing the chemical signatures in its atmosphere that we were only just learning to read. The silence was not proof of absence. It was proof of looking in the wrong place. SETI had been listening for radio signals, but the rest of the universe was quietly breathing in the depths of its oceans so that we could not hear. Being developed at the European Space Agency, aims to launch in the mid-2030s and will expand this observational reach even further. This is not a fantasy. This is a series of funded and planned instruments, building on each other, where each generation can answer the questions the previous one could only ask. This is concrete evidence that the answer is on its way. Paradigms were shattered. Billions of new worlds emerged. Our most fundamental assumptions about our place in the universe were shaken. and the silence itself became the greatest evidence. The Black have emerged. These were the biggest, fastest, most dizzying discoveries in human history. In just a few years, our understanding of the universe changed more than it had in the previous 3,000 years. But now, stop. Just stop for a moment and breathe. After this maximum speed, after this bombardment of epic moments, it is time to slow down. Because this discovery is not just about stars, telescopes, and numbers. It is about us. It is about looking in the mirror, and the reflection we see there is no longer the same. So, what does this new, vast, crowded, but silent universe mean for us? What do we do with this knowledge? How does this knowledge change who we are? Because the real question is not what is out there. The real question is, how does knowing there is something out there change everything here? And the answer to that question, but now it is time to stop and think. After this maximum speed, after this epic bombardment of moments, it is time to slow down. Now, it is time to stop the engine, get out of the car after this dizzying journey, and stand quietly under the stars. Because this discovery is not just about stars, telescopes, and numbers. It is about us. It is about looking in the mirror, and the reflection we see in that mirror is no longer the same. And now, we face that most important, most fundamental question: what does this new, vast, crowded, but silent universe mean for us, for you? What will we do with this knowledge? How does this knowledge change who we are? It all begins with a paradox of distance and proximity. On one hand, there is a distance beyond comprehension. 124 light years. Even light, traveling at the universe's absolute speed limit, takes 124 years to cross that distance. The fastest spacecraft ever built by humanity, New Horizons, would need about 2.5 million years to reach K2-18b. At that speed, we can never go there. We can never touch it. We can never have direct contact with anything there. This is a tragic, insurmountable reality imposed on us by physics. It is a forever unreachable neighbor. But, on the other hand, there is an incredible proximity. A scent, dimethyl sulfide, the breath of the ocean, one of Earth's most primitive, most biological, most intimate signals, Webb, did not send us a picture. It brought us that familiar smell you get while standing on an ocean shore from 1.2 quadrillion kilometers away. How can this be possible? How can such an absolute distance and such a deep proximity coexist? This is our new cosmic condition, physically completely disconnected, but chemically, perhaps more connected than we have ever been. Perhaps the real purpose was not to go there. Perhaps the real purpose was not to talk to them. Perhaps the only purpose physics allows was to know that they exist. And this knowledge alone, without contact, without travel, without any exchange, is enough to rewrite philosophy, theology, and science. Just as it was for Europeans in the 15th century when they learned of the existence of the American continent, they did not go there. They did not speak to anyone. But that knowledge changed their maps, their theology, and their understanding of humanity forever. You know that smell from the ocean too, perhaps on a vacation, perhaps in a coastal town. You have breathed in that smell. Now, the next time you smell it, stop and think. That smell no longer belongs only to this planet. It is an invisible bond you share with a world 124 light years away. At that moment, you too will feel how vast, and at the same time, how small the universe is. And this brings us to a second paradox, time itself. On one hand, there is the incomprehensible age of the universe, 13.8 billion years. On the other hand, there is our fleeting existence, gone in the blink of an eye. If the entire history of the universe were compressed into a single calendar year, all of human civilization would appear in the last 18 seconds of December 31st. And we, in those fleeting 18 seconds, built the James Webb. We sent it 1.5 million kilometers away. We cooled its mirrors to 40 degrees above absolute zero. And with it, we read the chemistry in a planet's atmosphere. The tragic truth is that we are the archaeologists of the universe. We can only read the past. The DMS signal that Webb analysed left K2-18b in the year 1901. In that year, the Wright brothers had not yet flown. The atom had not yet been split. The word galaxy meant nothing other than the Milky Way. We are reading the light of that era. We will not know what is happening on K2-18b right now until the year 2149. Perhaps that planet is now dead. Perhaps a giant stellar flare has destroyed its atmosphere. Perhaps its biosphere has already collapsed. And we are looking at the memory of something that is long gone. This is a permanent uncertainty we can never resolve. But the beautiful truth of this story is right here. For those 13.8 billion years, no life form had ever known another across the stars. No one. Nowhere. And then we came. In those fleeting 18 seconds. And we have the chance to be the first life form in the history of the universe to recognize life on another world. We are not the first to wonder. We are not the first to search. We might be the first to find. And you are living in that very moment. You are a part of those 18 seconds. You are a witness to this cosmological event. The shortness of our existence does not make this moment less meaningful. 8, on the contrary, it makes it infinitely more precious, more miraculous. But this witnessing confronts us with a third paradox, that fine line between knowledge and mystery. On one hand, we have the power to answer the oldest question in human history. This question has been the subject of philosophy, religion, and dreams for thousands of years. It could be debated, but not measured. But now it can be measured. Thanks to James Webb, this question is no longer philosophical. It is experimental. There is a measurement protocol, a confidence threshold, and a timeline. This is an irreversible revolution. No future generation will face this question without the option of searching for data. This is one of the greatest leaps in the intellectual history of humanity. The tragic truth is that this power has plunged us into more uncertainty. Every answer gives birth to 10 new questions. Is the signal real, or a calibration error? Is it biological, or from a geological magma ocean? Is it DMS, or DMDS? When will the telescope time be approved? When will we reach 5 sigma? The absolute certainty we seek still seems to be slipping through our fingers. It is as if the universe is giving us a secret, but taking it back at the same time. But the beautiful side of this story is that the journey itself may be more important than the destination. Perhaps the real discovery is not finding the answer, but proving that the answer is findable. The real victory is to take that question out of the foggy realm of philosophy and bring it under the bright light of science. Because this tells us that we are in control. This shows that the mysteries of the universe, no matter how great, are not beyond the reach of the human mind. You experience this in your own life. You start with a simple question, but as you search for the answer, you realize how complex, how layered the topic is. But this does not discourage you. On the contrary, it makes you even more curious, because learning itself is more exciting than knowing itself. And as humanity, we are at exactly this point. We have just begun the greatest lesson of the universe. Distant but close. Fleeting but decisive. Knowledgeable but still bewildered. These are the contrasts that define our new place in the universe. These are the new philosophical landscapes that K2-18b has opened up for us. But this landscape has layers. This is just the first glance. Beneath this reflection there is a more fundamental, more personal, perhaps more comforting layer. This is not just about our relationship with the universe, but about our relationship with each other. Because this discovery redefines not only our place in the sky, but also our place on Earth. And that new definition was perhaps the most surprising of all. Because this discovery redefines not only our place in the sky, but our place on Earth, our connection to each other. It's a definition that questions not only our relationship with the stars, but also what it means to be human. It means seeing our own reflection in a cosmic mirror, and in that reflection, seeing something we had never noticed before, a common destiny and a common vulnerability. And this is the most human layer of the story. This begins with that deepest paradox between loneliness and togetherness. On one hand, there is the incomprehensible silence of the universe, the 60 years of deafening silence from SETI. If the darkest interpretations of the Fermi paradox are true, meaning that intelligent life either destroys itself or never emerges, then we are mentally all alone in this universe. That is the tragic truth. There may be no one else to talk to philosophize with, to share our art with. This is an incredible weight on the shoulders of our species. This is the responsibility of being a single source of light in a dark ocean. This is a deep and inconsolable cosmic loneliness. But the beautiful truth of this story is that this very discovery offers an antidote that could cure that loneliness. Because if the universe is filled with microbial life on worlds like K2, 18b, this includes us in another kind of family. They may not be intelligent, they may not be technological, but they are also life. They are our distant relatives, born from the same chemical processes, subject to the same laws of physics. This is a different way of saying we are not alone. We may not have intelligent neighbors, but we have living cousins. And this emphasizes not our loneliness, but our kinship. It positions us not as the masters of the universe, but as just another, perhaps more complex, branch of the tree of life. This takes away our hubris and replaces it with humility. You cannot choose your family either, but you have a bond with them. As humanity, we did not choose this newly discovered cosmic family, but we have a bond with them, and this bond fundamentally changes who we are. This means we are no longer just human, we are earthlings. And this earthling identity confronts us with another contrast, that immense tension between individual effort and collective legacy. On one hand, there are individuals like you and me. We had no direct role in making this discovery happen. We did not design the James Webb. We were not one of the thousands of engineers who built it. We were not one of the hundreds of scientists who analyzed the data. This is a tragic separation. While the greatest adventure in history unfolds, we may seem like mere spectators. This can make you feel outside the events, small and powerless. But the most beautiful truth of this story is precisely this. Because James Webb is not the work of a single person, it is not even the work of a single company or a single country. It is a monument to collective human genius, built by thousands of minds, hundreds of institutions, and dozens of countries over decades. It is humanity at its best. And you are a part of that collective legacy. You may not have built that telescope, but that telescope was built with the accumulation of your ancestors' knowledge, your culture's heritage, and your species' progress. That knowledge does not belong only to scientists, it belongs to all of humanity. That knowledge is now in your mind, that curiosity is now in your heart. You did not invent the language you speak, but you express your deepest thoughts with it. You did not build the internet, but you connect to the world with it. You did not launch the James Webb, but with its eyes you look into the deepest secrets of the universe. You are not a spectator. You are the ultimate audience for which this incredible play was written, the ultimate consciousness where this discovery finds its meaning. When you face all this information, all these contrasts, all these new realities, what do you feel? Do you feel more connected to the universe or more alone in it? This is a question everyone must ask themselves, and both answers can be correct. Perhaps you feel a sense of loneliness and insignificance, realizing how vast the universe is and how small we are. This is very natural, but perhaps, seeing that we can read the chemistry of a world 124 light-years away, that we can smell its oceans, you feel a deeper connection to the universe than ever before. This is also very natural. Perhaps the real power of this discovery is that it can make us feel both emotions at the same time. It both humbles us and elevates us. It shows us both how small we are and what great things we can achieve all at once. This is like stepping into adulthood. You understand how complex and challenging the world is, but you also realize that you have the power to forge your own path in that world. As humanity, we are perhaps stepping into our cosmic adulthood, and this is both frightening and incredibly exciting, distant but close, fleeting but decisive, alone but together, individual but collective. All these philosophical reflections are the new intellectual landscapes that K2, 18b, has opened for us. They reveal not only the scientific but also the human dimension of this discovery. We now know that the universe is not an empty place, but potentially full of life. We now know that we are not the standard model of this universe, but an interesting exception, And we now know that understanding our place in this vast cosmos is not just about looking at the sky, but also about looking within ourselves, at who we are. This discovery held up a mirror to the universe, and in that mirror, we saw a face of ourselves we had never seen before. But in this reflection, in this philosophical deepening, there is still an undiscovered layer. This is not just about how we see the universe. This is about what it means for the universe itself. Because at the very end of this whole story, in the deepest part, another question awaits us. This question is no longer about searching for life. This question is about the meaning of life itself. And the answer to that question could change everything. A, B, so, lu, ti, li, everything. Because this story is not just about finding life on another planet. This story may be about why life exists in the universe. And this question, the question of why life exists in the universe, brings us to the final, deepest, most personal layer of our entire philosophical journey. This is no longer about what the universe is telling us. This is about what we are telling the universe. This is not just about understanding what our place is. This is about what we transform that place into. Because this discovery does not just give us information, it holds up a mirror to us, and the reflection we see in that mirror places a responsibility on us. Now, it is time to face that final responsibility, that final contradiction. It all begins with that most fundamental paradox about meaning itself, the indifference of the universe and the human search for meaning. On one hand, there is a completely indifferent, mechanical universe, a vast machine that has existed for 13.8 billion years, operating according to its own laws of physics and chemistry. For this universe, dimethyl sulfide is just a molecule composed of a sulfur atom and two methyl groups. Nothing more, nothing less. Its presence in K2-18b's atmosphere is no more meaningful to this universe than ammonia in Jupiter's atmosphere or argon in Earth's. It is just chemistry, just physics. The universe does not care what this signal means to us, because the universe does not know a concept called meaning. That is the tragic truth. All the excitement, all the curiosity, all the existential questioning we attach to this discovery is a one-way conversation. The universe will not answer us, because it does not even hear the question. This is the truth that the universe's greatest secret is, in fact, not a secret. It is just there. But the most beautiful, most miraculous truth of this story lies right here. It is not the universe that creates meaning. It is us. We are the consciousness that looks at that indifferent chemistry, gives it a name, dimethyl sulfide, writes a story, a potential biosignature, and attaches a meaning to it. We are not alone. We are the universe's way of knowing itself, understanding itself, watching itself in awe. A molecule is just a molecule until we interpret it as a sign of life. At that moment, that molecule transforms into a possibility, a hope, a revolution. The only thing that has this power is consciousness. You do this in your life every day. You look at a sunset. It is just the rotation of the Earth and the scattering of light in the atmosphere. Just physics. But when you look at it, it transforms into a work of art, a moment of peace, a source of inspiration. What makes it meaningful is not the sun itself, but your gaze. What makes the signal from K2-18b meaningful is also not the universe, but our gaze. And this gaze, this awareness, brings us to a second contradiction, the tension between the burden of knowledge and the strange bliss of ignorance. On one hand, if there is life on K2-18b, it is most likely a life that is not self-aware. Microorganisms floating in an ocean do not have an existential crisis. They do not question their place in the universe. They do not wonder if they are alone. They just exist. Their metabolism works, they reproduce, they die. This is a pure, unfiltered existence. Perhaps this is a kind of happiness, the bliss of ignorance. The tragic truth is that we can never have this happiness, because we know how big the universe is and how small we are. We are aware of our own mortality. This knowledge is a heavy burden. It is staying awake at night, looking at the stars and asking what all of this means. It is feeling the weight of cosmic consciousness on our shoulders. But the most hopeful truth of this story is that this burden is also our greatest gift, because the ability to ask why is what makes us human. This curiosity gives birth to art, philosophy, science, and love. Yes, this awareness can bring us pain, but it also gives us beauty, depth, and meaning. A microorganism can never compose a symphony, write a poetry, or build an interstellar telescope, because all these are the products of a mind that confronts the pain and curiosity of existence. You too, when you learn a hard truth in your life, sometimes wish you didn't know. Yet, you prefer to know the truth, rather than live in a lie, because knowing, no matter how painful, is liberating. And as humanity, we are beginning to learn the greatest truth of the universe, our place in it. This is the knowledge that will set us free. But this knowledge leaves us at the very heart of a third paradox, the most modern, most technological paradox: the power to see and the impotence to intervene. On one hand, we have the most incredible technological achievement in human history, the power to read the atmosphere of a planet 124 light-years away, to detect the chemicals there with parts per million precision. We are like cosmic doctors who can diagnose the potential biology of that planet. We can listen to that world's breath. The tragic truth is that we are doctors who can only diagnose but never treat. We are cosmic voyeurs. We know that the planet's star could flare up with a giant explosion at any moment and destroy it. We know that the planet's climate could enter an irreversible greenhouse effect and boil its oceans. But we are powerless. We can only watch. If the life on K2-18b is dying, we are helpless spectators. At a funeral, we will only watch with a 1-4 year delay. This is a deep, overwhelming impotence we feel in the face of this incredible power we possess. But the most shocking and beautiful truth of this story is that this impotence itself can be a moral act. The act of worrying about something so distant, so useless to us, something we are not even sure exists, shows what it means to be human. This is expanding our circle of empathy beyond our planet, our species, even beyond the known forms of life. This is the purest expression of universal compassion. We cannot save that planet, but our worrying about it can save us, because it shows that we are not just intelligent, but also conscientious beings. You too, when you see a disaster happening thousands of kilometers away on television, feel sad even if you can't do anything. At that moment, in that impotence, you become part of the collective conscience of humanity. The concern we feel for K2-18b is exactly that. And this is perhaps the most powerful signal we send to the universe. We are the ones who create meaning. We are the ones who carry the burden of that meaning. And with that burden, it is we who feel compassion for a distant world. All these internal journeys bring us to the door of one final question. Should this knowledge, this new cosmic position, change not only our thoughts but also our actions? This is no longer just about what we feel. This is about what we will do. And this brings us to a final philosophical layer, a final reflection. This is not just about our place in the universe. This is about our responsibility on this planet. Because this new discovery does not just show us what is out there, it also reminds us of how precious a thing we have here. And that reminder is perhaps the most unexpected, most jarring, and most important gift of this entire cosmic journey. Because this discovery doesn't just show us what's out there, it also reminds us how rare, how fragile, and how precious a thing we have here on this pale blue dot. And that reminder brings us to the final layer of all these philosophical inquiries, that last moment where we confront not the universe, but ourselves. This is no longer just about what we know. This is about what we will do with what we know. This begins with that most poignant paradox between the ordinary and the miraculous. On one hand, there is a world we live in every day, take for granted, and often forget. Traffic, bills, the daily hustle. In this ordinariness, we forget what an UNB-Liveable anomaly the planet we live on is. That is the tragic truth. While we search for life in the universe, we often see our own life-filled planet as a resource, a property, something to be consumed. We overlook what a rare jewel, our oxygen-filled sky, our oceans filled with potable water, the soil we walk on, and the incredible biosphere formed by millions of species surrounding us truly is among the hundreds of billions of planets in this galaxy. We are like lost souls living on a treasure while going on a treasure hunt. But the most transformative and beautiful truth of this story is that looking at a distant world, like K2-18b, shows us our own home anew. Searching for the scent of a potential ocean on another world reminds us of the value of our own oceans. Searching for signs of life in another atmosphere teaches us how precious our own atmosphere is. That distant, pale point of light is actually a mirror held up to us. And in that mirror, like astronauts seeing the Earth for the first time, we are left speechless by its boundless, blue and white beauty and fragility. Perhaps the greatest purpose of searching for life in the universe is not to find other life, but to understand the value of our own. You too sometimes pass by without noticing a flower blooming, a bird chirping, the smell of soil after the rain. But the existence of K2-18b reminds you what great miracles all these are. And at that moment, you realize that the greatest secret of the universe is actually under your feet. And this secret brings us to another, perhaps the most ultimate contrast, the search itself and the indescribable change that finding would bring. On one hand, there is this whole journey: curiosity, doubt, excitement, disappointment, the slow, methodical, sometimes frustrating progress of the scientific process, decades of telescope construction, thousands of hours of observation, millions of lines of code. The tragic truth is that this search could last forever. Perhaps the signal from K2-18b will never reach 5 Sigma. Perhaps there will always be a degree of uncertainty, a shadow of a doubt, and we will live on the brink of the answer, but never fully reaching it. This is to be stuck in a kind of intellectual purgatory, stuck between knowing and believing. But the most powerful, most hopeful truth of this story is that the search itself can be more transformative than the finding, because this search brought us together. This search united thousands of people for a cause that transcends national borders, political differences, and cultural divides. This search brought out the best aspects of humanity: our curiosity, our perseverance, our ability to cooperate. And if the 5 Sigma confirmation came tomorrow, what would happen? The world would change. Our paradigm would change. Not, but perhaps the real change has already happened on the path to that moment. The real revolution began the moment we turned the telescope to the sky. Because that moment, we proved that as a species, we can come together to seek answers to our deepest questions. You too try to reach a big goal in your life. Sometimes the satisfaction you feel upon reaching the goal pales in comparison to what you learned, the adventures you had, and the friendships you made along the way. Because sometimes the journey is more important than the destination. And this cosmic journey of humanity is our greatest adventure so far. After this entire journey, after traversing all these scientific, philosophical, and personal layers, we are left with the ultimate question the source text asks us at the end. If the 5 Sigma confirmation came tomorrow and the existence of life on K2-18b was confirmed, if you could ask those living beings a single question, what would you ask? This is not a simple question. It's a question that reveals what is important to you, what you are curious about, what you want to know on behalf of humanity. Maybe you would ask a scientific question. How did you evolve? Maybe a philosophical one. Is there a purpose to your existence? Or maybe a much simpler, much more human question. Are you lonely? The answer to this question is personal. And perhaps what's important is not what you ask, but that we have reached the point of being able to ask this question, because the act of asking this question itself defines who we are. It is the most meaningful signal we send to the universe. We are a life form that not only exists, but also wonders, questions, and seeks meaning. And that is perhaps the rarest and most precious feature in the universe: distant but close, fleeting but decisive, alone but together, ordinary but miraculous, seeking meaning but creating meaning. All these thoughts are the landscapes of the new universe that K2-18b has opened to us. We now know that our place in the universe is far more complex and far more interesting than we thought. We now know that the greatest secrets of this universe can be solved not only with telescopes, but also by looking within ourselves. And we now know that at the end of this cosmic adventure, we are discovering not just another world, but ourselves. This long journey, these dizzying discoveries, these deep philosophical inquiries have brought us back to the starting point. But we are no longer the same people. The sky is no longer the same sky. and this pale blue dot is no longer just a planet. It is now the sanctuary of a species whose only known home is in the universe, and who now stands on the brink of learning that perhaps it is not alone. And this knowledge changes everything. Absolutely everything. Now, with all that we have learned, with all that we have felt, it is time to stop one last time, look at the stars, and find the ultimate meaning this incredible story holds for us. The search for life on K2-18b showed we can solve the universe's secrets. But there's something I haven't told you. The universe's greatest monsters, black holes, may be destroying information forever. This was Stephen Hawking's greatest battle. In our next journey, we will descend into the heart of the black hole information paradox. Are you ready to save the most fundamental law of reality